Namaskar, my dear friends. Let us talk about digital logic design. So, in this session, what we'll try to understand is we will try to see various types of logic gates like NOT gate, AND gate, OR gate, NOT, NAND gate, NOR gate, XOR gate, XNOR gate. So, all these gates, their truth table, their formulas, and how these logic gates are actually applicable in our gate examinations. So, we'll start with one by one. So, let us start with NOT gate. So, what we'll do is let us see we have NOT gate. So NOT gate, as you can see, what happens is suppose we have input A and output Y. Okay, so A can take value 0 1, and since it is NOT gate, it means if it is 0, NOT means output will be 1. If it is 1, NOT means output will be 0. Just the opposite of that. Okay, it means Y is going to be equal to A bar. Okay, it means A is 0, so Y will be A bar, that is 1. Its symbol is basically like this. So this is my NOT gate, this is my A and this is my Y, and Y is nothing but A bar. So what it means is, let us say we have NOT gate here, and let us say we have input as, let's say like this. So we have, let's say, V input, this is my logic 1 and this is my logic 0. Alright, so you can see this is 1, this is 0, this is 1, like that we have. So what will be my output? My output will be like this. Whenever the input is 1, my output should go to 0. Whenever my input is 0, output should go to 1. So like that, it is just opposite of that. So this is my V output. Understood? So this is the thing all about my NOT gate. All right. Now let us talk about AND gate. So in AND gate, what happens is we will first understand like what it is. I already told you, 0 means low or it is off. Okay, or 1 means high and it is on. Okay, so this is the thing that you have to take care of. Okay, now AND gate, what it does is, let us say we have input voltage here, which is, let us say, my V input. Now we have a resistor and we have here, let us say, a bulb. Now what is going to happen is, let us say we have two switches and this is my switch A and this is my switch B. Now can you tell me what will be my output, like whether the bulb will glow or not? It will depend on both the position of A and B. So A and B are switches. So what happens basically is, let us say we have A, B and we have Y. So A and B can take positions like 0 0 0 1 1 0 1 1. Now any of the switch, either or both of them are open, it means the path is not complete, so bulb will not glow, it means it will be 0. So either both of them is 0, it will be 0, or any one of them is 0, then also it is 0, because the circuit is not complete. If both of them are closed, it means both of them are going to make the circuit on, and this is how you are going to get Y. Understood? So this is your input, which is AB, and output is your Y. Now AND gate is represented like this. Okay, so this is my A, B, and this is my Y. And Y, the expression is going to be Y is equal to AB. Okay, so it is a multiplication of A and B. Now what happens is, let us say input side or output side, what you can do is, let us say we have 1 0 1 0, like that, 1 0 1 0. So this is my, let us say, V input, and accordingly you will see your output will be also flowing. Okay. Anyway, it doesn't matter. What I will tell you one more thing is, can you write down the expression for Y in terms of max terms? So yes, where this is a min term expression, right? If we try to write down max term expression Y, then wherever 0 is there, that term we will take. So 0 is here and we'll take this one. So it can be A plus B. Then Next is A plus B bar, because 1 is B bar, right? So A plus B bar into A bar plus B. So this is another expression for AND gate. So this is very simple expression, y is equal to AB, and this is another expression in terms of max term expression for y equal to AB. Now I'll tell you one more thing. This is called as enabling expression and disabling expression. Okay. So let us say we have the AND gate here, and I am going to put this as 1. So which is called as enabling input. Enabling input. Now what will happen? Whenever the other input goes to high or low, based on that I can have my output high or low. So let us say if my other input is 0, my output will be 0. If my other input is 1, my output will be 1. So basically this is going to be enabling input. So keep one of the input as 1 and the other input will be able to control the output. So this is how it is called as enabling input. Let us now talk about disabling input. So what happens is, one of the pin, if you keep it 0, so this is called as disabling input. So what happens is, let us say if you keep other term or other input as 0, what will be the output? That will be 0. Now if you keep other input as 1, still the output will be 0. Why? Because it will never be on if the other input is 0. Okay. So that's the reason this is called as disabling input. So in short, you can write down enable input, enable input is equal to 1 and disable input, input is equal to 0. Okay. So if you keep one of the pin as 0, then it will be always 0. Okay. Good. So this was my signal which can be considered as high, low based on this thing. Okay. Now let us talk about OR gate. So AND gate is done. We can now talk about OR gate. So OR gate, what it happens is, let us say we have a circuit, like we have input plus minus and we have resistance here, and then a bulb is there. Now what is going to happen is, the switch are connected like this, A and B. Okay, so this is my switch A, this is my switch B. Now can you tell me what will happen to the bulb Y? So whenever one of the switch is on, this will start glowing. Why? Because that path will be taken. Okay, so the path will be taken into account. Understood? Similar to that, if both are off, then only it will not glow. Okay, the path will not complete. So this is OR circuit. So you can see my table can be written as A, B and Y. So 0 0 0 1 1 0 1 1. Now my output will be, when both are 0, then only it will be 0. Otherwise any of them or both of them are on, my output will be always 1. Understood? So you can see, if I take the output expression y is equal to, if I see max term expression, so wherever it is 0, that term I can take. So it is nothing but A plus B. So y is equal to A plus B. This is my OR gate expression. Okay. Otherwise, in mean term expression, another thing what I can do is, wherever it is 1, I can see as mean expression and mean term expression. And this mean term expression can be expressed as A bar B plus AB bar plus AB. So I can write it down as A bar B plus AB bar plus AB. So this is another expression for OR gate. And OR gate symbol is actually like this. So in digital electronics, this is like this. A little bit curve at the input, and that's all. So this is my A, B and Y. Okay. Now similar to the enabling input and disabling input, we can quickly see here. So let us say we have the OR gate. We have the OR gate. Now, if I talk about enabling input, so what will happen is, let us say this is 0. So what will happen is, if I keep my other input as 0, my output will be 0. If I keep other input as 1, my output will be 1. It means if we held one of the input as 0, the output will depend based on the input of other inputs, right? Similar to that, there is a possibility of disabling input. Okay, so what happens is, let us say I keep it 1, so that will be considered as disabling input. Now if I keep my other input as 0, my output will be always 1. Why? Because 1 0 is 1. Now if I keep my input as 1, then also my output is going to be 1. It means my output is not changing, it means it is disabled. Okay, so this is how you have disabling input as 1 and enabling input as 0 for OR gate. Okay, now let us talk about other gate. Now let us talk about NAND gate. So what we will do is, we will see NAND gate. So what does it mean is, basically it is nothing but opposite of AND gate, okay, or complement of AND gate. So what happens is, let us say the symbol of AND gate was this, okay. Now what we can do is, for NAND gate we will be having a node here, okay. So this will be NOT. So my input is A, B and output is Y, and my output is going to be A, B, and since we have put a negative sign, so A, B bar. So this is the expression for my NAND gate, okay. And as you can see, if by De Morgan's theorem, you can also see that Y can be written as A bar plus B bar. So this is another expression. So what is the truth table for this? You can have A, B, Y, and my input can be 0 0 0 1 1 0 1 1. Now my y will be opposite of AND gate, right? So whenever AND gate was, whenever input was any of them or both of them was 0, the output was 0. So now those terms it will become 1. So 1 1 1 and this will become 0. So this is the thing. Now what we can do is, we can see here my y can be written in terms of mean term. So y can also have another expression for NAND gate. Wherever you are seeing 1, this thing can be written as A bar B bar plus A bar B plus AB bar. So this will be the expression for NAND gate. So A bar B bar plus A bar B plus AB bar. Okay. And as you can see, the other expression was max term expression, which is A bar plus B bar. So you can see A bar plus B bar is this, and by De Morgan's theorem you can convert this into this form. So this is the most popular form or most popular expression for NAND gate. Okay, now NAND gate is nothing but a combination of AND gate and NOT gate. So you can see we have this as AND gate, and if you put one more NOT gate, so this is my NOT gate that we have studied. So this total put together is going to be called as NAND gate. Okay, understood? So for enabling input or disabling input, if you want, so what will happen? The enabling input will be 1 and disabling input will be 0, because as you can see, any of them or both of them are 0, the output is always 1, so this will be always disabled. And if one of them input is 1, output can go to 0 or 1. Okay, so that's the reason it is enabling input is 1 and disabling input is 0. Now let us talk about NOR gate. So since we have talked about AND, then NAND, then OR we have talked about, now the opposite of OR will be NOR. Okay, NOR gate. So in NOR gate, the expression is like this. This is the symbol for NOR gate. OR gate, opposite of that is NOR gate. So this is my A, this is my B, this is my Y. Okay, and Y is going to be equal to A plus B, that is OR, and opposite of that or complement of that, that is my NOR. Okay, so this can also be replaced by or written by Y is equal to A bar into B bar. By De Morgan's theorem, you can see Now let us say we will talk about truth table. So suppose we have A, B and output is Y. So what is going to happen? 0, 0, 0, 1, 1, 0, 1, 1. So we had seen that if both the inputs are 0, my output was 0 for and 0 for OR gate, right? So it is opposite of that. So what will happen? That will become 1 and rest all will become 0. Okay, because any of the input is 1, the output is 1 for OR gate, and for NOR gate that will become opposite of that. So this will be a NOR gate. Understood? Now if you try to write down the expression for like a NOR gate, so wherever mean term is there like 0, we can write down the expression. So what we can do, as you can see, uh, for mean term expression, wherever 1 is there, output is like a bar b bar. So it is saying a bar b bar, and by De Morgan's theorem you are going to get y equal to a plus b whole bar. Now in max term expression, if we see wherever 0, those terms we can consider. So what will happen? For y equal to 0, this is a plus b bar. So like that I can write down y equal to a plus b bar into a bar plus b into a bar plus b bar. So you can see wherever 1 is there, that will be bar, and wherever 0 is there, that will be without bar. Okay, so this is the another expression for NOR gate. Okay, now very important thing that you have to understand is this NAND gate and NOR gate are also called as universal gate. Why? Because they can be used to convert into any gates. Okay, so my NAND gate and NOR gate, okay, NOR gate are also called as universal gate. Okay, why? Because any logic gates can be implemented, because gates can be implemented using these two gates. Okay, using NAND gate and NOR gates alone. Okay, so only by using your NAND gate or only by using your NOR gates, you can implement any of the gates, whether it is AND gate, NOR gate, NAND gate, or like NOT gate, OR gate. Any gates are there, you can implement them. Now we'll talk about very important other gates which are called as XOR gate or XOR gate. Okay, so let us talk about XOR gate. So it is also called as XOR gate, or it can also be called as sometimes XOR gate. So in this XOR gate, the symbol is like this. So what it says is, let us say we have input A, B and output is my Y. So Y is actually written as A XOR B. So XOR is actually plus sign and then a circle around that. Okay. So let us say if we talk about truth table, it can be A, B and Y. So let us say it can be taking 0, 0, 0, 1, 1, 0, 1, 1. So what will be the output? So the output is going to be 0, 0 is going to give you 0 and 0, 1 will give you 1, 1 and then again 0. So if both the inputs are same, it will be 0, and both the inputs are opposite, complement to each other, then it will be giving you the expression 1. It means you can also write down a definition. My XOR gate actually produces output 1 only when odd number of inputs are ones. Okay, so you can see number of ones in this is 1, so it is giving you 1. Number of inputs is 1, so it is giving you 1. Number of inputs are 2 here, so it is giving you 0. The number of inputs are 0 here, that is also a even number, so that's the reason output is 0. Understood? So let us say quickly, if we want to write down the expression using this particular terms, so in terms of min term and max term, we can write the expression. So let us write first min term. Wherever we will see 1, my output will be what? To tell me. My output will be this a bar b plus ab bar. So basically my XOR gate is ab bar or a bar b plus ab bar. Okay, or otherwise it can also be written in terms of max term. So wherever 0 is there, that way we can see. So it is 0, it means a plus b into a bar plus b bar. Okay, so it can also be written as a plus b into a bar plus b bar. So this is the another expression for XOR gate. So mainly this is the expression that is most like commonly used, which is a bar b plus ab bar. Okay, now can you quickly tell me, if there are three inputs a b c, what would be my output for XOR gate? So basically like a XOR b XOR c, if I want to do, so let us say we have, what are the different options of the input? So we have 0 0 0 0 0 1 0 1 0 0 1 1 1, then we have 1 0 0 1 0 1 1 1 0 1 1 1. I told you the odd number of inputs are 1, the output will be 1. So just keep that in mind and you can quickly write it down. So here it is going to be 0, then 1, 1, it is going to be 0, it is going to be 1, 0, 0, 1. Understood? Because 3 ones are there, so we have odd number of ones. We have only 1, so like that. Wherever odd number of ones are there, I am going to get my output as 1. Okay? Now, a little bit of properties for this XOR gate is, if A XOR B, if you want to see, then it will be equal to B XOR A. Okay, so it is commutative property. Now, if you want to find out A XOR B XOR C, so you can also do that. That you find out A XOR, first you find out B XOR C, and then you do XOR operation with A. Otherwise, you can also do that A or B, and then you do XOR operation with C. So for three variables, you can do that and you can get the same results. If you do not remember this, for two variables, you find out the result and then do XOR operation with third one. So it means wherever it is equal, it will be 0. Wherever it is opposite, it will be 1. Okay. Now let us talk about more properties in XOR gate. So what we are going to do is, this XOR gate, let us say we have this XOR gate. Okay, so what will happen if we keep here 0? What will be the output dependency? So can you tell me, if I keep 0, the output will be 0. If I keep our input as 1, the output will be 1. It means my 0 is acting as a enabling input, because output depends on the other input. Now let me tell you another thing. If I keep same XOR gate and put one variable as 1, like tie one of the input as 1, so what will happen to the output based on other variables? So let us say if we keep 0, the output will be 0. If we keep 1, the output will be 0. It means either you give one of the variable as 0 or one of the variable as 1, the output is actually like getting getting changed. Understood? So both of the time it acts as a enabling input. Understood? Now what is happening here? Can you see that it implies, the first one you can see, whenever it is 0 tied, the 0 is giving you 0, 1 is giving you 1, so it is nothing but acting as a buffer. So can we write it down? Let us say this is my gate, XOR gate, and this is tied to 0. So if my input is A, whether it is 0 or 1, my output will be same A. Okay, if it is coming 0, so 0 1, so 1. So this is acting as a buffer. So if you want to like implement a buffer using XOR gate, you tie one of the input as 0, the other input will be giving you the output same as input. Now let us see this one. So what is going to happen here is, if we see, this is my XOR gate that is there, and one of the input is tied to 1. So what is happening? If we tie this to 1, my 0 is becoming 1 and 1 is becoming 0. It means if my input is A, my output is getting inverted. So it is nothing but inverter application. Okay. So inverting application. It means if you want to find out the negative output by giving a output and you want to invert the output, you can tie one of the input to 1 and you will get your output negative or opposite of the input. It means what can I write in the conclusion? I can write as both 0 and 1 act as a enabling input. Okay. Both logic 0 and logic 1 acts as enabling input. Understood? For XOR gate. Now let us talk about quickly properties of XOR gate. So you have to understand that there are a lot of gate questions that are being asked based on properties of XOR gate, and this is very important. So you can put it VVI. Okay, put a triple star mark in this. Okay, so what is going to happen is, let us say number 1, A XOR 0. Okay, so A XOR 0 is nothing but A, and A XOR 1 is going to be A bar. So you can see A XOR 0 is A and A XOR 1 is A bar. Understood? Then if we talk about A XOR A, if both are same, then it is going to give you 0, and A XOR A bar, A XOR A bar, if it is opposite, then it is going to give you 1. Understood? So this is how you are getting an understanding of, if both the inputs are same, the output is 0. If both the inputs are complement to each other, the output is 1. Now if we have 3 A's, let's say A XOR A XOR A. So whether it is 0, then it will be 0. Whether it is 1, then it will be 1. Okay, so it means if triple A's are there, it is going to give you 1. So what does it mean? It means I can write it down A XOR A XOR A XOR like n times. Okay. So what will happen is, it will give me A if n is odd. Okay. So whether it is 0, then it will give me 0, 1, that will give me 1. That is if it is n is odd. If n is even, then what will happen? The number of ones will be always even. In that case, it will be 0. Got it? Now let us talk about another properties. So properties of XOR gates are, third one, we have A XOR A bar B. Okay, so this is going to give me A plus B. Understood? Now we are going to get fourth one, AB XOR BC. This is going to give me AB XOR BC is just like that, B times A XOR C. So it is like B can be taken common to this. Understood? And fifth one, you can say A bar B XOR AB bar. Okay. So you know A XOR B is nothing but what? A XOR B is what? A bar B plus AB bar. And I am going to do XOR operation between A bar B and AB bar. So this will give me A XOR B. So this is the beauty. Okay. Now let us prove one of them so that you can have an understanding how it is going to work out. So let us say third one I want to prove. So what is going to happen? A's or A bar B is nothing but this is a formula for A's or B, right? So using that I can write it down as what? I can write down as A into or A bar B, right? So A bar B plus A B bar. So B bar is nothing but A bar B whole bar. So this is how you are going to get. Got it? Now if you expand this term, what you are going to get is A bar into A bar is nothing but A bar B plus A times, this is going to be by De Morgan's theorem, it is going to be A plus B bar. So if I solve it quickly, it is going to be A bar B, I'll write it down like this, A bar B plus AB bar. Okay, and this if I take B common, or what shall I do, A common I will take. Okay, so we have A bar B plus A I will take common, so it is going to be 1 plus B bar, and you know already 1 plus anything is 1, so it is just A. So we are going to get A plus A bar B, right? And this one you already know that it is going to be A plus A bar into A plus B, and you know A plus A bar is 1, so it is going to be just A plus B. So as you can see, A's or A bar B is nothing but A plus B. Understood? If you want, you can prove same way this fifth one. So let us say I'll just solve fifth one quickly. So what is the JOR operation of this? So JOR operation of this is going to be A bar B XOR A B bar is nothing but this expression we will use. So A XOR B is A bar B plus A B bar. So same way this will be A bar B bar, okay, like A bar B. So A bar, the whole term is considered as A, like A bar B is considered as A, and A B bar will be considered as B. So A bar B I will write plus A B bar. So A into B bar. B bar is A bar B whole bar. Understood? Now what we are going to get here? This is a very good expression. If you want, you can prove it by yourself as well. Pause the video and try to do it by yourself. Okay. Now what will happen? We can write it down as A plus B bar into A B bar by De Morgan's theorem, plus here we are going to get it as A bar B into A bar plus B. Got it? Now if we multiply that, we are going to get it as uh, A B bar plus A B bar. Okay, 2 times. Understood? Because A into A is A and B bar, and this here also A into B bar. Now another one we are going to get it as A bar B plus A bar B. So redundant terms are there, you can get rid of them and you can simply write it as A B bar plus A bar B, like two times are there, so we can write one time. Okay, and this is nothing but your A's or B. So it means A's or A bar B's or A B bar is equal to A's or B. Understood? You can prove fourth one by yourself. Now let us talk about XNOR gate. Okay, so what happens is we have XNOR gate, or it is also called as XNOR gate. Okay, so it is nothing but opposite of, or like the complement of XOR gate. Okay, so if we have inputs like, let us say, A, B, and output is Y, then it can take up 0 0 0 1 1 0 1 1. So the output will be complement of XOR gate, right? So whenever it is equal, it will be 1, and opposite it will give me 0. So that's all. So how does it look like? My output Y is represented as A XNOR B. So it is circle and then one dot. So this is how it is, like represented. Understood? So it is A XNOR B. And the symbol for this is like this. There is a dot over the output. So this is going to be A, B, and this is going to be Y. And my Y will be what is the expression from the truth table that you can find out? So let us say if we take mean terms, then we can see the result. So mean term is nothing but wherever it is y, wherever it is 1, we'll take those. So it is going to be a bar b bar plus ab. So my y will be a bar b bar plus ab. Okay, got it? For this one we are going to have a bar b bar, and for this one we are going to have a b. Now if we try to write down using max term, my y can be become what? Wherever it is 0, we will take those terms. It will be a plus b bar into a bar plus b. So it is going to be a plus b bar into a bar plus b. So this is how we have the expression for XNOR gate. Okay. Now one more thing what we can do is, we can see from the result that my XNOR gate can produce or produces output as 1 only when see, so my output will be 1 when number of inputs are 1, and that is also even number of times. So basically when even number of inputs are logic 0. Okay, we'll talk about zeros. So even number of logic zeros are inputs, then output will be 1. Okay, so when even number of inputs are logic 0. So if logic zeros are even number of terms, then you will get output as 1. So in the XOR gate, we had seen odd number of inputs as 1. In XNOR gate, even number of inputs as zeros. Okay. Now some of the properties that you can see. Before that, what we can do is A XNOR B, it is going to be equal to B XNOR A. Okay. And then A XNOR B XNOR C is going to be equal to commutative property, so that our associative property, so it is A XNOR, you do the operation between B and C first, then you can also do that A XNOR B first, and then do the XNOR operation with C. Okay. Now let us talk about, like enabling and disabling input kind of thing. So what will happen is you can see you can see let me talk take here, or will take down. So what is going to happen is, let us say this is my XNOR gate, right? So we have XNOR gate symbol like this. Now let us see, one of the input we tie it to 0. So what will happen to the output? So let's say if we are going to have input as 0, my output will be 1, because even number of zeros are inputs, right? And then if it is 1, then output will be 0. So what it is going to give me? It is nothing but if my one of the input is 0, and another input is, let us say, A, so 0 is becoming 1, 1 is becoming 0. So it is nothing but your A bar. Understood? So this is nothing but your inverting application. Got it? So if the other input is 0, the other input can act as inverter. Understood? Now same way we can take up one more time. Let us say we tie the input to 1. Now we will try to observe what is the output that is going to happen when input changes. So if it is 0, my output will be 0. If it is 1, my output will be 1. So it is nothing but your buffer application. Okay. So if it is 1, my input is, another input is A, the output will also be A. So this is nothing but your buffer application. Now let us talk about some of the properties of XNOR gate. So these are very important properties. Okay. So what we'll do is, let us say first one, if we talk about A XNOR 0, okay, A XNOR 0. So you see here A XNOR 0 is A bar. It means it is going to give you complement. Similar to that, if I do A XNOR 1, then it is going to give me A. It means it is a buffer application, okay. Now if you do A XNOR A bar, so if both are opposite, then output will be 0. And if A XNOR A, then it is going to be A only, because if it is 0, then it will, no, sorry. If A XNOR A, then it is going to give you 1, okay? Because both the zeros, then it is 1, both the ones, then it is also 1. But if number of inputs are more, let us say A XNOR A XNOR A XNOR, like that, n times. And this is very important one, okay. So this will be giving me what, like if n is odd, okay, then it will always be A, whether it is 0 or it is ones, right. And if it is going to be n is even, then it is going to give you 1. So it means what, like if n number of times you put a's or a, then it will become 1 always whenever the number of terms are even, and if number of terms are odd, then it will be a, okay. Now another properties is, if a XNOR a bar b, just like we did for XOR gate, so what is going to happen is it will become a plus b, same way, okay. And a b XNOR b c, so this is going to give me same way, b will be common, so b into a XNOR c, understood. And if we talk about another one, a bar b XNOR a b bar, then it is same just like XOR gate, a XNOR b, understood. So these are the three properties that is there for XNOR gate. Now if we talk about more properties, so fourth one, we have a bar XOR b, that can be a XNOR b. So relation between XOR gate and XNOR gate. And if we do that, similar to that, a XOR b bar, this is still my a XNOR b, understood. So either you do a bar XOR b or a XOR b bar, both will be giving you a XNOR b. Now let us say, if I am going to talk about a bar XOR b bar, so this is going to give me a XOR b, okay. And if I talk about next one, a bar XNOR b, so just like a bar XOR b, so now we'll talk about a bar XNOR b, so it is going to give me a XOR b. So this is very important, okay. Similar to that, a XNOR b bar, so this is going to give me a XOR b, okay. And a bar XNOR b bar, it is going to give me a XNOR b. So opposite of, like XOR gate, it is going to give you this one. So this you can take it as seventh, okay. Now we will talk about a little bit more into logic gates, that is nothing but alternative logic symbols for logic gate, okay. And this is very important. So in this session only we'll try to finish up that one as well. So we'll write it down as alternative logic symbol for logic gate. What does it mean? What does it mean is, like we have, let's say, AND gate. Is there any possibility that we can represent this AND gate with another symbol? So yes, there are possibilities. So what is the rule that we will see first? The rule is you have to convert your AND to OR, okay. Your AND to or to AND, okay. And another rule is put a bubble, or that is not, okay. So put bubble on each input lines, okay, and on each output lines. So you have to put bubbles on each input lines and each output lines, okay. And so this is my first one, this is my second one, and third one is like it is not applicable for XOR gate and XNOR gate, okay. So this is not applicable for XOR gate or XNOR gate. Understood? So let me just give you quickly. So what does it mean is, let us say we have AND gate. So this is my AND. So how it can get converted into other form? So it will be equivalent to, we have to do that AND is becoming OR. So how OR is made? Like this. Understood? So this is my OR. And we have to put bubble on each of the input and output lines. So how it will become? It will become like, we have to get like this and like this. So this is my bubbled NOR, okay. So the AND gate is actually this one. So you can see this is NOR gate and bubbled input. So this is bubbled NOR. Similar to that, if we have OR gate, this is OR gate, what would be the equivalent? Can you find out by yourself? This is going to be first and then bubble input as well as output, okay. So this is how bubbled NAND. It means I can tell you directly that my AND gate is equivalent to bubbled NOR gate and OR gate is equivalent to bubbled NAND gate, okay. And if we have NAND gate, so what will happen? This is my NAND. So this is going to be equal to, this is OR because it is AND type, and then bubbles, bubble, it will become no bubble, and then this is like this. So this is going to be bubbled OR gate. Similar to that, we have NOR also, one more. So we have this one as NOR. So this is going to be equivalent to first and without no gate at the output, and input will be bubbled. So it will be bubbled AND gate. Got it? So now it is very clear to you like how we can represent our logic symbols as some other alternate logic symbol, okay. So other alternative logic symbol you can have like this. All right guys, so we will see questions based on these questions. A lot of gate questions have been asked in previous year papers from electronics communication or electrical engineering or computer science, as well as like instrumentation engineering. So we'll try to solve questions in the next session. Thank you.